No? Yes? 53? Oh, okay, Quiz B, yeah, I don't mind doing that. So the problem was u equals v minus 5 over v squared minus 18. And we're supposed to find the domain. How's the lighting? Is this too bright? How are we? I know right in the center it's... You're okay? You can turn off the middle. And then maybe, can you just... Well, are y'all okay like that or what? You just let me know if it's too dark, all right? Okay, so the denominator, right, is what we're concerned about here. There are no square roots, so we don't have to worry about that. So just the denominator, we want to make sure it's not equal to 0. Now, to solve this quadratic, you can move your 18 to the other side. This is one way, by adding 18 to both sides. And then you can take the square root on both sides. And when you take the square root of the left side, it'll get rid of the squared. When you take the square root of the right side, you get square root of 18, but it has to be plus or minus. Because anytime you take the square root on both sides of an equation, you have to do plus or minus. So what you get here is v cannot equal, what is it? Plus or minus. Yeah, it depends on you. You could leave it at square root 18. I would have been fine. You could have turned square root of 18 into 3 root 2, or you could have even done a decimal. I don't care what you would have done there, all right? I'm going to leave it at square root of 18 because that's the exact answer. That's what it is. Whatever that is, that's what it is. So I need to make sure that my answers are not that, right? So I go to my number line. I have two numbers, negative root 18, whatever that is, and positive root 18. I know for sure that the negative is on the left of the positive, right? So I can do that. I do not want those, so I'm going to put open circles there. But it can be anything else. So it can be anything to the left, anything in between, anything to the right. Yes? You don't have to. Mm-hmm. Yep. Plus, with what we're going to do today, this kind of leads into what we're going to do today with the drawing. So how do I say everything up to negative root 18? Negative infinity. Negative root 18. Parentheses. So that gives me everything up to negative root 18. Then we use the union symbol, everything past negative root 18 on. So I say parenthesis negative root 18, all the way till I get to where? All the way till I get to positive root 18. So parenthesis again. And then union, last one, root 18 to infinity. That's what I was looking for. Or replacing all the root 18s with 3 root 2. Or what is it as a decimal? 4 point something? 4.24. Okay, any of those would have worked. Okay, good. All right, let's get going with some new stuff. So we're still in 2.4 in the book. We're still talking about functions. I want to talk real quick about the vertical line test. You might hear me refer to this in the future as the VLT, vertical line test. In my experience in teaching, this is probably the one thing that most students get right almost 100% of the time, and that's applying the vertical line test. What the vertical line test does is it gives you a way of testing to see whether or not a graph is a function. So this test determines if a graph, that means a picture that someone's giving you, is a function or not. So is the graph a function or not? If anyone watched the video last time, I had forgotten to plug my microphone in. So it was the microphone off the laptop, and you could hear every single time I hit the screen with my pen. I apologize about that. It's a bit annoying, but I'm plugged in this time. So this test determines if a graph is a function. So let me give you a graph first, and then we'll determine if it's a function using the vertical line test. So there's a graph. Question is that graph representative of a function? So what we do with the vertical line test is we draw vertical lines. And the rule is that any vertical line that you draw cannot hit the graph more than one time. So you see I drew that line, right? How many times did I hit it? One time. That's okay. I draw it again. Any vertical line I draw can only hit one place. Any vertical line, only once. Does it seem like that's going to happen? Every single time I draw a vertical line, I'm only going to hit one time? Yeah. As long as that happens, it is a function. Okay? So the way we write that mathematically is if any vertical line intersects or hits graph no more than once, then it is a function. Remember, function, when we talked about function last class, we talked about the idea that a function takes an input and spits out an output, right? Input, output. This function, well, this is a function because it passed the vertical line test, which means that for every input that I plug into this function, which we don't know what it is, it spits out exactly one output. So let's take a look at something that would not pass the vertical line test and therefore would not be a function. Oh, I should put something on top of this so you know that it is a function, right? This one is yes. This is a function. But the one below it that I'm about to draw, a circle. Okay? Does a circle represent a function? That means for every input, for every x I plug in, is there exactly one output? Well, I start drawing some lines. So how about the line I draw over here? That's okay, because the rule says I can't hit it more than one time. What if I don't hit it at all? It's fine, as long as it's not more than once. How about the one that I draw that comes right here and touches just that corner point, which we would call a tangent line? That's okay also, because I hit it once, right? It's as soon as I start to draw any lines inside the circle that I hit two times, right? And that's where I violate the rule. And therefore, this twice means no, not a function. So if I give you some drawings, ask you if it's a function or not, you apply the vertical line test. Is that okay? All right. The next thing that we want to make sure we're clear on when it comes to functions is evaluating functions. So how do we evaluate functions? Well, we're going to do an example. Let's let f of x, that means I'm defining a function, equal negative x squared minus 4x plus 7. Whoa. I don't want it to ask me later. I'm sure. So there's a function, right? We call that the explicit definition of the function. Can anybody tell me what the domain of that function is? Everything, right? All real numbers. Good. Because there's no fraction, there's no square roots, right? I'm not asking for that, but just every function we see now, we should be able to at least entertain that thought. Okay, so here's what we are going to do. Just practice evaluating. So if I ask you to find f of 2, I'm telling you plug in 2 for all your x's, right? Just replace all your x's with 2's. So it'd become negative 2 squared. Watch the way I write this. 2 squared. Then minus 4 times, here comes my 2, and then plus 7, right? That's what I'm doing. All my x's became 2's. I'm going to change something over here. There. So what is it? 2 squared? You get 4, but then there's a negative in front, right? So it's negative 4 here. The important thing to notice on that is I put that 2 in parentheses, didn't I? Right here. And that's because the squared happens before the negative in front. So you square the 2 first, make it 4, and then you come in and change it to negative. You'll see on the next example that I'm going to do how that's different if you plug a negative in. Now, what about the negative 4 times 2? What do we get there? Negative 8, and then plus 7. So what's that, negative 5? So that means if you plug in 2, the function spits out negative 5. Great, who cares? That's what happens. Now let's find something else. How about we find f of negative 1? So negative, and then I'm plugging in negative 1 squared, then minus 4 times negative 1, right? Then plus 7. So now that negative 1 is actually going to get squared first, right? What's negative 1 times negative 1? Positive 1. But then there's a negative in front of it. So it's going to basically remain a negative 1. Then plus 4? Plus 7. So what do we got here? 10. Okay. Most of us have evaluated functions, right? Seen that somewhere before? Okay, how about this though? Same function. Find f of negative 2m. So now I'm plugging in a variable, right, with a number in front of it, but it's still replacing all my x's with that. So I will have the negative that was sitting there, then in parentheses, what? Negative 2m, and I'm going to square that. Then subtract 4 times what? Negative 2m, and then add 7. What happens when I take the negative 2m and square it? What's negative 2 squared? Positive 4, and then what's m squared? M squared. So just the red parentheses with the squared there becomes 4m squared. But then you have a negative in front. So it's negative 4m squared. Then what? Plus 8m, plus 7. Now you can't do anything to this, okay? Like all the other answers, you know, negative 5, 10, you had a number because we plugged in a number, didn't we? Number in, number out. Here we plug in an expression with a variable. It's going to spit out an expression with a variable because it doesn't know what m is, okay? So that's our answer. We'll do one more. How about find f of x plus h? Now think through this, okay? What this is saying is to plug what in for x? x plus h. So everywhere you see an x, you're going to replace it with x plus h. So I'm going to rewrite everything again. I have my minus, but then I'm plugging in what? X plus h, that whole thing, squared, right? Minus 4 times that whole thing, x plus h, and then plus 7. Do y'all agree? Now, we need to clean this up, okay? This is not, this is what you get when you plug in, but it's not simplified out. So let's try and do this slowly. Let me take the x plus h squared, right? That x plus h squared there. Let me do that as some scratch work on the side here. What is x plus h squared? Careful. You can't square each one individually because of the plus sign in between. You have to do the FOIL. So does that look familiar? 2 terms times 2 terms, you multiply those. The first multiplication, x times x gives you x squared. X times positive h gives you a positive xh. The inside, h times x is still x times h. And the outside, plus h squared. Do we have a lot of Cowboys fans in here? Cowboys fans, raise your hand. Okay. I don't like the Cowboys at all. So. How about Breaking Bad fans? Any Breaking Bad fans? Okay, we're good now. We're back on speaking terms. Okay, so I'm simplifying this. What does it become? X squared plus 2xh plus h squared. Do not make the mistake, okay, on the test. This is how you lose a lot of points on a test, is taking that and saying it's x squared plus h squared. Okay, I mean, that's just a common mistake, but it's a mistake that you can't make in this class. All right, because later on, we're going to be doing lots of things with that, and if you mess that up early in the problem, it's everything after that's going to be wrong. So be careful with that. Now, that's just what that yellow part is, right? What do we have sitting in front of that yellow part? Negative sign. So that negative is like a -1, isn't it? So it's going to take everything we just got here in yellow, and it's going to change the sign of everything. So I'm ready to come back over here and plug in. This equals, how about -x squared minus 2xh minus h squared. Does everyone see that that is the yellow part with a negative distributed to every term? Yeah? Now let's continue. We had not done the -4 distributed through that x plus h. So we get what there? -4x minus 4h. And then we still have tacked on to the very end of the problem plus 7. Now you look at that and you see, do you have any like terms? Do you have anything that you can combine together? No. What does it mean to be a like term? Like, what would we have to have in order to put those together? Same exact variables. Each term would have to have the same variable raised to the exact same power, right? Okay, so none of those are like terms. So therefore, that's our answer. You don't need to worry about rearranging the order. Like some teachers will say, like, put all your x squareds, and then you would do the minus h squared, and you try and do some sort of descending order. But it's hard when you have multiple variables to get a proper descending order. So you can just leave it. All right. Okay, I'm going to give you the rest of the homework assignment from 2.4, and we're going to move into the next section. So it starts on, well, we'll go page 202. You should do 37 through 45. all. Now that seems like a lot of problems, but that's just they give you a graph and you do vertical line tests and say yes or no, it's a function or not. So that should take you all but maybe 2 minutes to do it if you understand the vertical line test. Then do numbers, where is it? Numbers 69, 71, and 72. Those three problems are basically what I was just doing, plugging things into a function. So just take your time through those. All right. We are done, and we are going to, even though I don't want to do this, we are skipping 2.5. I'm not sure why, but I think it's because this class is a terminal college algebra class, right? Like nobody needs more math after this. So we skip 2.5 because it's more than what you would need. Okay, we're just trying to get the bare minimum here. So that's a good thing for you, but it kind of makes me cringe a little bit. 2.6. This one's called this section's called the toolbox of functions. And transformations. And let me just tell you what this is about first, and then we'll get into it. This section, when they say a toolbox, like you think of toolbox, I've got a little toolbox at home that I have in my garage that has like, a hammer and a screwdriver and different things, right? Everyone has the idea of what a toolbox is, right? The kind of essential stuff that you need if you're going to work on something. The toolbox of functions is basically the functions that every college algebra student needs to know. You need to have this in your mental toolbox. You need to know what these look like without having to refer to anything. And then later on, as we're doing more advanced problems, you'll be like, oh, that's that function that I have in my toolbox. I know what that looks like. And once you have that toolbox of functions, you can then just transform them and make more complicated functions out of them. So that's where we're headed. So what is the toolbox of functions? Well, it's 1, 2, 3, 4, 5, 6 functions. What's that? Transformer 6? We're going to transform all 6, yes. The toolbox consists of 6 functions that everyone should know. The first one is called the identity. No. And it is the function f of x equals x. Why do they call it the identity? What's f of 1? What's f of 2? What's f of k? What's f of a dog? Right? Basically, whatever happens here, whatever you plug in, right, is what comes out. It's identical. The input is identical to the output, isn't it? So if you were to graph this function, let's look at the input and output as ordered pairs. If I plug in 0, what comes out? 0. So this is my in and my out, right? Everyone's seen this before, like X and Y, input, output. Is that all right or no? Anyone? So what would that point be on my graph? Right in the middle, right? We call that the origin. Now let's do another point into this identity. One goes in, one comes out. Where would I plot that point? How do I plot it? Right one, up one, right? So I go right one, up one, I put a dot. Then I go what? 2, 2, right 2, up 2. And I keep doing this, right? 3, 3, 4, 4, 5, 5. I could even do negatives, right? Let's do a negative one. Negative 1 spits out negative 1. So that would go to the left 1 and down 1. Can y'all see what it is? It's just a straight line. What you could have told me already, if you recognize this as being like an mx plus b, what's the m? What's the slope of that line? 1. And what's the y-intercept? 0, right? We did lines already? No? Did we do lines? I thought we did lines. Okay, well, y equals mx plus b is the equation of a line. So we could have recognized that if we recognize it as a y equals mx plus b. But that's the graph. So everyone in your toolbox, the function f of x equals x is a diagonal line, right? Perfectly diagonal line that passes through the origin, isn't it? I mean, that could be a quiz question, right? Real quick quiz, first thing next class, right? Sketch f of x equals x without a table, with nothing. Just draw me the picture. That's an intense quiz, I know. Okay, the next one is called the absolute value. This function is very similar to the identity, except that instead of x, it's the absolute value of x. Didn't you? For a domain problem? Yeah, so, but the domain of an absolute value, there's no restriction, because you can take the absolute value of any number. You just can't take the square root of a negative, and you can't divide by 0. Okay, so you were, all right. Maybe you hadn't seen those before. So those little lines on the outside of the x are the absolute value symbol. What does the absolute value symbol mean? Yeah, all the absolute value does is says spit back, basically give me the positive answer of whatever's in there. So let's try and plug in some numbers here. If we plug in 0, then what comes out is the absolute value of 0. The absolute value of 0 is what? 0 itself. So we have another point at the origin. We plug in 1, what's the absolute value of 1? 1. So this is looking pretty close to the identity. Plug in 2, we get 2 again. Right? 3, we get 3. 4, we get 4. So it's looking like it's the same thing as the identity until we try a negative number. When we try negative 1, we get positive 1. So that means I go to the left 1, not down 1, but up 1 now. And then if I try negative 2, the positive answer of negative 2 is positive 2, right? So I go left 2, up 2. And then you go negative 3 would be positive 3, negative 4 would be positive 4. And so what you get is a line going the other direction, like this. What's that? Yeah, it's like a mirror. It's like a reflection. Now, that looks like a V, right? And I want everyone to look at it as a V, not a U. Okay, there's no, it's not curved down there like this. It's a hard corner. That's what's happening with the absolute value function. So now that's in the toolbox. You have a V, the absolute value is a V with the corner of the V where? At the origin, okay? That origin is going to be something common to all of our toolbox functions. All of our toolbox functions will go through the origin. It's just, you need to remember which part of it goes through the origin. That all right? Next one. The third function is the squaring function. And we did study the squaring function when we first started talking about functions. It's the one that squares whatever you plug in. So you plug in number, it squares it. X squared. All right, let's plug in some points. Plug in 0, what do you get? 0. So we have a point at the origin. You plug in 1, you get 1 squared is 1. All right, so that's looking like the identity, isn't it? So far? But then you get to 2. 2 squared is 4. So at 2, I'm up 1, 2, 3, 4. And I'm not going to go any further, but what would the next one be? I'm not going to plot anymore, but 3 would be 9. So now it's way up there off my chart. Now let's try some negative numbers. Negative 1 squared would be positive 1. So negative 1, positive 1. Negative 2 squared would be positive 4. So that again is looking like a mirror, right? Like a reflection. Here's the difference though. They aren't lines. Okay? The things connecting these dots is curved. It's not a straight line. So when we draw this, it'll look more like a U than a V. And it does go through the origin. Most of you have heard of that or looked at that before and called it a parabola. That's what it is. It's a parabola. But I'm here talking about a specific parabola, the parabola x squared. That one goes through the origin, has a certain curvature to it, all right? That's what it looks like. All right, halfway there. The fourth one, the square root. This is f of x equals the square root of x. That's kind of like the opposite of the squaring, right? The third toolbox function, the squaring one, we took what was there and we squared it. Here we're taking what's there and taking the square root of it. So we're going to talk about them later as being inverses. They undo each other, but let's take a look at what the function is going to be. So let's start out with some points. How about 0? What's the square root of 0? 0. So we have the origin again. Let's plug in 1. What's the square root of 1? 1. All right, so it's, again, starting to look like the identity. Square root of, so I'm not going to plug in 2. I'm going to think about it first. 2, if I plug in 2, what's the square root of 2? Whatever it is, square root of 2, 1.414. Okay, let me try 3. Plug in 3, square root of 3, I don't know. 4, square root of 4 is 2. So I'm actually going to go out 1, 2, 3, 4, and I know that the square root of 4 is 2. And I'll put that as my ordered pair. 4 goes in, 2 comes out. What's the next one you would know? 9, right? 9 would be the next one, so I'd have to go way out there. So I'm not going to, but I'll write it down. If I did 9 on my x, I would have to go up 3. The question is, what's happening on the negative side? So let's try and plug in negative 1. You can't. That's right, because you cannot take the square root of a negative number, or negative 2, or negative 3, right? Which means that there is no graph over there, which means your graph only exists over here like this. Now the arrow means that it continues like that, okay? It's very important for you to understand that on the square root function, on the toolbox square root function, it starts at 0 and goes to the right. There's nothing to the left. And if I had asked you for the domain of this function, if I did, I haven't done that, but the domain of this function, if you were to do it, would be from 0 to infinity. And you can kind of tell from the picture that it goes from 0 to infinity, right? That's where the picture exists. All right, next, there's 2 more. It's the cubing function and then the cube root. Those are the last 2. All right, so the fourth one, the cubing, fifth one, yeah, sorry. Cubing, it's f of x equals x cubed. And the sixth one, I'll leave some space here, is the cube root. And that's f of x equals the cube root of x. Now I'm going to draw the pictures of these on the side, but I'm not going to plug points in because I think you get the idea. You could just plug points and get your dots and figure out what it does? The cubing function goes through 0, 0. It comes up on the right like a parabola and goes down on the left kind of like a parabola. That's what the cubing function does. The cube root function has a point at the origin, and then it goes like this. Well, it's kind of like it's kind of like the one on top, but laid on its side and kind of flipped over or something. You have a U shape. See, you have a U shape here, and you have a U shape here, like this. The thing about the cube root is we can have negatives in cube roots, right? If I tell you what's the cube root of 8, what's the cube root of 8? Cube root of 8? 2. But I could, no, that's the thing. Cube roots, it's only the cube root of 8 is 2 because 2 times 2 times 2 is 8. But the cube root of negative 8 is negative 2 because negative 2 times negative 2 times negative 2 gives you negative 8. So you have to be a little careful. With odd roots, if it was cube root or fifth root or seventh root or ninth root, any odd root, you don't have to do plus or minus. If it's even, then that's where you have to look at two possibilities. All right. I should also say, for any even root, you couldn't do a negative inside. All right, so those are the toolbox functions. Now, how are these going to help us here? Well, now we talk about transformations. We're going to have a time to practice today. Formations. Transformations. Dun, 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 dun. All right, I'll teach you a mathematical symbol that you may not have ever seen before. A capital S with a little line on the bottom like that. Has anyone ever seen that before? No? That stands for the word suppose. Okay? Suppose you know the graph of a function f of x. So all that's saying is, hey, let's just pretend that you know what this function f looks like. I'm not telling you what it is. Let's just say you know what f looks like. When you draw it on a piece of paper, you know exactly what it looks like. Then, here's the result. F of x plus some number, c, shifts f up by c. So that means you know what this function f looked like. If you add a number to it, all it's going to do is take that graph and move the whole graph up by that much. And what do you think will happen if I subtract c? It shifts it down. These are what we'll call vertical transformations. Or sometimes they're referred to as vertical shifts. You're shifting the graph up or down. So let me give you an example of this. Sketch the function f of x equals square root of x plus 2. Now, when you look at this, don't be all distracted by the fact that this function's called f, and earlier I said, let's act like you know what f looks like. What I want you to do is focus on what is in here. What is the function defined to be? It's the square root of x plus 2, right? Do you know, or do you see a toolbox function in there? Yes, what's a toolbox function? The square root of x. So you know that right there, that's from your toolbox. You know what that looks like, don't you? So all you're going to do is take that function that you already know and add 2 to it. So adding 2 should move that picture that you know up 2. So here's how I'm going to do this. I'm going to take a graph, and I'm going to, in very light pencil, do a dashed line version of, that's what my toolbox looked like, right? That's what the square root of x looks like, toolbox-wise. And I'm going to exaggerate the origin, right, with 0, 0. Every point on that graph now needs to go up 2. So let's say that that's 1. Let's say that that's 2. Just take every point and move it up 2. So you're going to, I'll do it in a different color, even though you can't. I'm going to move, that origin point is now here, right? And my graph now does this. And we are done. Okay? This is not about getting it super precise. It's a sketch. It's just a sketch. That's it. So the solid graph there is the answer. You do not have to put the dotted one on your answer. It's just to help guide you here. Is that pretty clear? What if it was -2? You would take that dot, pull it down. So I'm just going to put it here. If it had been -2, I would have gone here. And then don't stress out. I mean, just cross wherever you want. I don't even care about where across the x-axis. Just draw it. It's just a rough sketch. It would eventually, because that graph does keep going up and to the right. All right. So that's our up and down shifts. Those are the easiest ones. Now, how would you move a graph left and right? So let's see. So I'm returning now to my notes up there. If you have f of x plus c or f of x minus c. So let's see, what is the difference between my adding of a constant on those compared to the ones that we just did? It's going to move left or right, but I'm saying, where's my c? It's inside the function, isn't it? Look at the way I wrote that. See how I did f of x plus c and then I closed the parenthesis? That's extremely important. What that tells you is that that number you're adding is right there next to the x, inside the function, not on the outside. Like over here, right? That c is outside the function. Like when we had the square root of x, plus 2 was outside the square root, wasn't it? So I'm going to do the comparison here. Let me tell you what this does. This shifts f, what do you think? Left or right? Which one? Your instinct would say right, right? Because positive is this way. With left and right shifts, it is opposite of what you think. You have to remember this, okay? Up and down is what you think. Add up, subtract down. Left and right shifts, opposite of what you think. It's counterintuitive. Counterintuitive, that's the word we use to, when it goes against what you would initially think. So this would shift it f to the left by c. And this one would shift it right. You just have to remember it. These are called horizontal shifts or horizontal transformations. And let's do the same one as an example. I'll do that example of f of x equals the square root. We had the square root of x plus 2 a second ago. How would I write it so that I get a shift to be left or right instead of up or down? So square root of this time x plus 2 all under the root together. Do y'all see the difference? That's critical. The plus 2 is inside there with the x inside the squaring function. And that's what tells you left or right. And in this case, it is left. Opposite of what I think. So on my picture, my quick sketch, my original one started here. It looks like this. But I'm going to take that and move it left 2. So I grabbed the point that I know and I moved it to the left 2. Do y'all agree? Another example. Okay. I want you to think about this one. Nope. I want us to think about this in terms of toolbox. Okay, good. It's a squaring function. Can somebody tell me about the shifts, plural? Go ahead. Left 4, down 3. That's it. Now, sir, sorry to wake you, but to get yourself out of a 10-point penalty on our next exam, okay? You awake? Do you know how to graph that? Like quickly. I'll let you work on that. Everyone else graph it. See if you can just get a picture. Start off with maybe a dotted version of what you know it looks like, and then do your shifts. Anybody have it? Yeah. Raise your hand once you got it. Okay. All right. It should be quick. It should be quick. Now, as I do it, I want to bring up a point here. Does it matter which shift I do first? It doesn't matter in this problem, but it matters in general. So let me tell you the proper way to go about this. Okay, pay attention because this can get you into big trouble. You always do it like you do order of operations, starting with the x first. Like, look at the x. What's right next to the x? The plus 4. That means that shift comes first. Okay? Then I go outside the parentheses to the minus 3. So in this problem, it wouldn't matter. Down 3, left 4, right? Or left 4, down 3 gets to the same place. But as you'll see when we talk about next transformations, it can get you tripped up if you don't do them in the right order. So I'm going to go left 4, 1, 2, 3, 4. I'm going to draw another dotted version. So that's just my left transformation. And then down 3. So here's my point. It's going to come down 3, 1, 2, 3, right here. Here's my final version. It's here. I do not care where it passes through. That's it. Now, I'm going to proceed. There's 2 more transformations that you're going to need to know. There's more than that, but that's all I'm going to ask of you. So the last 2, so far we've had the function plus c or minus c, right? So up and down. We've had the c inside the function, which moved us left or right, opposite of what we thought. And the last one, the last two, I should say, is what if we just put a negative sign in front of the function? Or what if we put a negative sign inside the function? How does that change what we know? So this, the first one, the negative one here, flips f over the x-axis. Or if you don't like the word flips, it's a reflection. And putting a negative inside flips f over the y-axis. Or reflects, if you like. I'm wondering if I should give you the last one or if that's it. We'll do just these two. Okay, let's do an example now. So let's do f of x equals negative absolute value x minus 3, close the absolute value, plus 2. The idea here is that these should be pretty quick to sketch now, if you got your toolbox down. So when you first look at this, you say, do I see a toolbox function? What is the toolbox function here? Absolute value. Right? So you got the absolute value, right? We know that that looks like the V, right? Sharp corner. That's what absolute value looks like. So I know it's that graph, but what do I do with it? So let's go in proper order here. What would come first? We take care of the 3 first. The minus 3 inside tells us which way. Right 3. Right 3. Okay, that's what this tells us. Then, careful, next thing that would happen. Reflection. Because look, isn't this negative sitting in front here? Isn't that negative really like a negative 1 being multiplied? And wouldn't you do multiplication before addition? So it's almost like you start with the x and you work your way out. And the last thing you'll ever do is the plus whatever's on the outside, up or down. That's the last thing you'll ever do. So this minus right here gives us a reflection over which axis? X-axis. Okay? And then finally, the plus 2 out here, right, gives us what? Up 2. So we're going to take an absolute value function. We're going to move it to the right 3. We're going to reflect it over the x-axis. Then we're going to move that whole thing up 2. And that will be our picture. Here it comes. I'll do it in phases. First phase is what is my absolute value function just as is. Toolbox, straight out of the toolbox. Right 3 comes first. Y'all agree that moved me right 3? Reflect now. Reflect now. You do not want the plus 2 first. It would be different, okay? So next thing would be reflect over the x-axis. We haven't done a reflection, have we? So all you do to reflect is just flip it down, okay? So just flip everything over the x-axis. So I maybe can do this if I come up here. I'm going to take that V, and I'm just going to go whoosh, like this. So imagine, whoosh. You have to make that sound when you do it. So that's your reflection. And now that graph, where? Up 2. So I'm going to take that point. Remember that corner point, right? I'm going to take that point and pull it up 2. And this is going to be my final picture. I'll do it in red. So there's my corner point, and it goes down like this and like this. Now I'd like to show you something on the side here. If you had taken your V and gone to the right 3, like we were supposed to, and then moved up 2, like this, and then reflected, it would be wrong. Here's why. If I reflect this over the x-axis, this is my pivot point. So the whole thing has to come like this, like that. Do y'all see that? You don't reflect it right here. It's over the whole axis. So when I reflected that down, it would have wound up down here like this, which is not the correct answer. As you can see the one on the left. Do you see how that reflection is completely different than that one? So it's an order of operations thing, and you have to get it right, or else your picture can be wrong. So always work from the inside out. Okay, we're running out of time, but I think that's pretty good to get you started on homework. Yeah, this is good. Here's what I'd like for you to do. Page 237. I was going to give you some group work today, but there's just not quite enough time. 237. Try 31 and 33. Try 65. Through 73 odd. And then try 75 through 83. Oops. Odd. I guess I could have just said 65 through 83 odd. Let me tell you a little about these, okay? Because they're kind of weird. These two, what they do on 31 and 33 is they give you the graph and they tell you to come up with the function. So you've got to be able to see the transformations backwards. So those are going to be a little challenging because I didn't do any like that. 65 through 73, they give you the function like I was giving you, and they give you graphs, and it's a match. Match the graph to the function. So you have, it's like you have to choose between graphs A, B, C, D, E, F, G, and match it to, number 65, number 67. And then on 75 through 83, that's exactly what we did in class. They give you the function, sketch it. So on these last ones, do what we did here. We did in class. All right? That means you should write down the toolbox function and what transformations occurred and then draw it. Everybody, shall we take attendance? Does everyone look like they're here? Leslie, huh? Yeah. Let's just hang tight. Hang tight. We have 5 minutes. Just give me a chance to take attendance. Make sure you're sitting where you normally sit, please, because that's the way I'm going to take attendance. I can stop recording.